Okay, thank you very much. Pleasure to be here. So as this is a general Swiss map general meeting, the audience is quite varied, even though we will kind of do at least something directly or indirectly related to mathematical physics. So I purposefully tried to make the talk elementary or as elementary as possible. So hopefully I succeeded. Okay, so the topic is kind of very straightforward. So I'm looking at a one-dimensional stationary Schrödinger equation. So basically just a second order ODE. The important thing, of course, is that it has this parameter h bar squared, which will play an absolutely crucial role. So Q is the potential, which, if you're a physicist, maybe you're more familiar with an expression like this. And the point about the Schrödinger equation, as important as it is that it is very rare to actually be able to solve it in closed form. There are, of course, the famous harmonic oscillator with hydrogen atom, but that's more or less it. So kind of as soon as you start studying the Schrödinger equation, immediately becomes apparent that if you actually want to understand solutions, some kind of approximation methods perhaps are needed. And there's an even greater point to always keep in mind when you're studying the Schrödinger equation, which is that somehow you don't just want arbitrary solutions. You want special solutions, which are supposed to satisfy many properties. One of them is that they are aware of the classical limits, in the sense that when h bar becomes very, very small, somehow you should be able to see that behavior in the solutions. So in particular, that means the standard kind of existence uniqueness theory for ODEs that we learn in undergrad. Although you can do it in the presence of a parameter, but that theory tells you nothing about the behavior as h bar goes to zero, this asymptotic behavior as h bar goes to zero. That's what makes the problem difficult. So one of these techniques, one of these approximation techniques, is called the Wkb Approximation Method. And so although Wkb stands for Wenzel, Kramer, Brilliant, three physicists from 1926, they published this work. The method itself, in some form or another, actually goes way back to as early as Nouvelle, Green, in the 19th century. In fact, some textbooks even refer to this method as Nouvelle-Green approximation. And well, so the basic idea is that because we have this parameter h bar that we really want to keep track of, the idea is to try to solve the Schrödinger equation asymptotically as h bar goes to zero. So in particular, that means, especially if I'm a physicist and to me h bar has some very specific constant meaning, then I have to do away with that notion and pretend that h bar is a parameter. And so now I'm forcing myself to explicitly include the h bar dependence. So now I want some kind of analytic behavior in the h bar direction. And notice that I also put h bar in the potential, so in principle that could also depend on h bar in some bizarre way. Okay, so what's the method? The method is that you take this, so you take this limit as h bar goes to zero, you simplify the problem, and you look at the leading order equation corresponding to the Schrödinger equation. So the meaning of the leading order equation needs to be interpreted correctly here, but basically you can already see why that would simplify the problem, simply because if you look at this equation, what makes it hard is that it's a differential equation, and the parameter h bar appears only, it appears in front of what makes this equation into a differential equation. It is in front of the differentiation. So if I literally just set h bar equal to zero, then I should get some kind of algebraic equation, no longer a differential equation. Algebraic equations, of course, are easier. Right, so then basically I do that, I simplify the problem, I solve the leading order equation. Of course, that is not a solution to my differential equation. I need to correct it, and the corrections depend on h bar. And so the idea is that you add, in some kind of systematic, successive way, you add corrections, h bar dependent corrections, to get a true analytic answer at whatever non-zero value of h bar that you're interested in. And so what I just described is a very typical quintessential problem, singular perturbation theory. perturbation theory because I'm using the parameter h bar to perturb around the easy problem, which is this algebraic analog of the Schrödinger equation, which I can actually solve usually in closed form even. And I perturb and I try to get to a true solution of my hard problem, the one for non-zero h bar, by summing up successively contributions in h bar. And it's called singular perturbation theory because the nature of the problems that I'm interpolating between are very, very different. So for any non-zero h bar, this remains a differential equation, second order differential equation. So how the complexity is the same for any non-zero h bar. But as soon as h bar literally becomes zero, then it's no longer a differential equation, it's an algebraic equation. So the nature of the problem has changed completely. That's the meaning of the word singular. And well, okay, so I already mentioned that the notion or the meaning of the leading order equation needs to be interpreted correctly. That's one subtlety. But the other thing is that, of course, number two in this method is extremely, that's a very, very difficult, tricky step, which is what basically this talk is about. Okay, so here's how the Wkb method for the Schrödinger equation goes in detail. So imagine I'm studying this Schrödinger equation, second order ODE. The Wkb method starts with what is known as the Wkb ansatz, which is to say, I'm going to look for solutions of my Schrödinger equation in this special form, which is exponential of integral of some test function s divided by h bar. So I'm basically, I'm going to try to write down conditions on this test function s such that this exponential expression is going to satisfy the Schrödinger equation. And crucially, the fact that the exponent, the dependence on h bar is 1 over h bar, that's somehow the key feature of Wkb ansatz. And I'll also put a little minus here just to make some of the signs work out better. So, okay, so if you take this expression, so s is now the unknown function. If you take this expression, put it into the Schrödinger equation, compute a few derivatives, cancel the exponential, you get an equation, a first order, so no longer a second order, but nonlinear differential equation for this test function s. So that's this thing is called the Riccati equation, so it's quadratic. So it's the simplest nonlinear first order differential equation, and it's also singularly perturbed because the differentiation side of the equation is multiplied by my parameter h bar. So if I set h bar equal to 0, then this degenerated easy problem is no longer a differential equation. It's literally an algebraic equation for s. Okay, so the method is to solve this equation in power series of h bars. So I'm going to take a formal power series in h bar whose coefficients are some meromorphic functions of x or some kind of functions of x that I'm going to solve for. And I'm going to plug that in to this equation, compute it order by order. So here's the first couple of orders. So you can see the first equation is no longer a differential equation, it's just an algebraic equation, and it has an obvious solution, or it has two obvious solutions. You should just take the square root of q, the two determinations of the square root of q naught. Of course, those solutions, immediately you can see that the importance of avoiding places where q naught vanishes is important, because otherwise, well, the two solutions are no longer distinct and they have some kind of singular behavior, logarithmic singular behavior at those points. Those points are called turning points, and somehow they're infamous in singular perturbation theory. You always want to avoid, everything is kind of done away from turning points. And then the turning point analysis is a separate tin of cockroaches. Yeah, so easily, immediately get two leading order solutions, S naught plus minus, just the two determinations. And then as I continue expanding my equation in powers of h bar, one thing that you should note immediately is that these are no longer differential equations. Although there is differentiation involved, but you see here I'm differentiating the function that I solved for in the previous order, and that happens at every order. So I've now replaced my problem of solving a differential equation by a problem, an infinite tower, recursive infinite tower of algebraic problems. So no more integrals that need to be computed. And the other thing is, of course, so here the first order equation, of course, I would need to be solving for S1, which means, I would need to divide by whatever 2S0. And as long as S0 is non-zero, which we have already said previously, those points we should avoid. So as long as S0 is non-zero, I can divide the whole thing by S0 and I have no problem. So as long as I stay away from turning points, this successive, as soon as I choose a solution of the leading order equation, this entire tower just collapses. I get a solution for each level. So in other words, I can solve for a power series solution S hat. There's two of them, depending on which leading order solution I pick, S hat plus minus, and they give me two formal power series and H bar solutions with coefficients which depend on X.
Sorry.
Yeah.
One question, what is Q?
So Q here is it depends on H bar, so that's the leading order in H bar. So you can pretend that it's a polynomial in H bar or maybe a power series in H bar. More generally, it would be you take the asymptotic expansion. So that anyway, the limit as H bar goes to 0 of Q. Okay, so then by definition, once I found these formal expressions as hat, a formal Wkb solution is just this formal expression where I take this exponential and just put in the formal power series. So you're almost there. You've almost solved your Schrödinger equation. This is a solution. But the problem is that it's not a true solution. It really is a formal solution because these power series, S hat plus minus, in general are divergent. They have zero radius of convergence. So in other words, this expression kind of in a naive way cannot be promoted immediately to an analytic expression. So it really is just a formal object. So that's a big problem. And there's kind of three ways out of that problem. One is to, do formal analysis and just ignore all analytic aspects in the H bar direction, treat this as a formal symbol, and you can get some mileage out of it, lots of mileage. But of course, oftentimes you do want exact expressions or some kind of analytic expressions. So one easy way to cook up some kind of analytic object out of this formal procedure that I made is just to truncate the formal power series S hat. And so, for example, here, I just chose only the very much leading order of the power series, and that is this is obviously an analytic expression which you can work with, but it is obviously not a solution to my Schrödinger equation because if I plug it in, I won't get a vanishing. So this is the kind of the business of the exact Wkb analysis, which is how can you promote these formal Wkb solutions to actual analytic objects that have some analytic behavior in the H bar plane. The idea is this, that you take these power series S hat and you interpret them as asymptotic power series to actual solutions S plus minus without the hat. And then, so if let's say S plus is an analytic solution whose asymptotic expansion as H bar goes to 0 is S hat plus, then if I look at this object, which is now an analytic exact object, then this is going to be a solution, first of all, to my Schrödinger equation, an exact true analytic solution, whose asymptotic behavior is like this formal expression. One maybe a more precise way to say it is that, for example, this this truncation, this leading order truncation, psi plus minus naught, is really the leading order asymptotic behavior. So whatever, if you take the ratio or take the limit, that should be 1. So that's the idea. That's kind of the idea of exact WKB analysis, which is to try to promote these solutions these formal solutions S hat plus minus to actual solutions by using them as asymptotic expansions. So, another way of saying this this phrase that I said about the leading order asymptotic is that you really want you want an analytic function S plus minus whose asymptotic expansion is this formal power series S hat, and the leading order is fixed. Okay. Yes.
So at this stage, you're not taking into account any non-perturbative current up here.
So I think I am. I mean, I'm not quite sure what the definition of non-perturbative correction, but basically, I think that's the idea that a perturbative series is the formal Wkb expansion that I wrote.
Okay.
And then, in order for it to be promoted to an actual exact expression, you need to add non-perturbative corrections, and that's what this object takes care of.
Okay.
As far as I understand the meaning of non-perturbative corrections. Okay, so that's the idea. That's the procedure. Simple enough. The big question is, do these analytic functions S plus minus actually exist? Is there actually a pair of analytic solutions S plus minus to the Wkb equation whose asymptotics are S hat plus minus? And this is basically so that's the main purpose of what is known as exact Wkb, and there's been lots of work, especially since the 80s, with seminal work of Boros and also many very well-established Japanese schools. So there's many kind of partial results and examples and special classes of equations where this has been confirmed, that we know the criteria for when such solutions exist, but somehow the general criterion for existence of such solutions has not been done, so that's what my paper is about. Okay, so maybe the one point to emphasize is that the method that I use in my paper is kind of it's very powerful. That it's not only just the Schrödinger equations that I can tackle, it's I can consider much more general neuromorphic singular second order OD. So for example, here you see I've already added a linear differential term in my equation, and so normally the results that you find in the literature, they require the potential Q to be either constant in H bar or maybe a polynomial. So for me, I can easily assume that they are some kind of maybe convergent power series in H bar, or even more generally. So I don't want to get into these details, but more generally, if you know these words, then I can assume that PQ are they only admit asymptotic expansions in H bar equal to 0. So they could be some very, very complicated transcendental functions. And I just want to make sure that I fix the regularity of my asymptotic expansion to be some partial rate. But anyway, this sentence you can ignore. You can think that these coefficients P and Q are really just convergent power series in H bar with neuromorphic coefficients. Okay, so that's my equation. So if I do the same procedure as a couple of slides ago, I look at the Wkb ansatz, which is that I'm looking for solutions of psi in the form exponential integral S over H bar. Then this is the Riccati equation that I obtained. So you can see that on the right, I basically have a general quadratic polynomial in S. So I will solve the leading order part of that quadratic polynomial. So again, I take the limit as H bar goes to 0, the left-hand side, which is the differentiation, that dies. And all I'm left with is just a quadratic polynomial like this. So as long as I'm away from the 0 locus of the discriminant of this quadratic polynomial, then I can always find locally a pair of holomorphic solutions, S0 plus minus. So the turning points, which were the zero, if you remember for the Schrödinger equation, they were the zeros of the potential. Here in this more general picture, they become the zeros of the discriminant of this quadratic polynomial. So that's the direct generalization. And then using the exact same procedure as I showed you with the Schrödinger equation, you expand this equation in power series of h bar, and because we're staying away from turning points, we can solve the leading order equation, and then kind of it cascades down, and you can find the entire formal power series solution S hat plus minus, one for each leading order solution. Okay, so here are the criteria. So this is the theorem for existence, uniqueness of exactly unique solutions. So let me take a simply connected domain, and I want the discriminant of my leading order equation to be non-vanishing on that open set. Then there is this funny kind of condition, which is a very kind of non-local assumption on my equation. So even if I'm studying my Schrödinger equation and I really want some kind of local existence and uniqueness of these solutions with nice h-bar asymptotics, you find immediately that the condition for existence of local solutions has a non-local component. So more precisely, there is this analytic vector field, which is that I take the vector field d by dx, and I multiply it by the inverse of the square root of the discriminant. So it's some vector field, and I'll take a real part of it. It's a real analytic vector field. And the condition is that I need to take U and I need to flow it under this vector field. So of course, when you flow sets, that immediately becomes a kind of a non-local problem. What you want is that this flow of this vector field is complete. So in other words, the integral trajectories of this vector field, they don't encounter any singularities in finite time. Right, and then there's just a small kind of regularity assumption on the coefficients P and Q over this complete simply connected set U, which is that they need to be not quite bounded. Oh, I can move the hand. That's weird. So they don't need to be bounded. They just need to be bounded by this square root discriminant. So you should think that in the limit of the flow of on U of this vector field, the discriminant square root delta becomes singular. Maybe it has a pole at the end, or some kind of maybe transcendental essential singularity, something like that. So that means I'm really not requiring P and Q to be bounded in some way. I'm just saying that they at the end of the flow they don't blow up worse than the square root discriminant. Actually, from the point of view of differential geometry, this vector field is extremely natural, because if you look at the corresponding dual differential one form, it's just square root delta dx, and that is basically this generalization of the analog of the Nouvelle one form on the cotangent bundle. So this vector field is, well, in the paper I call it the Nouvelle vector field because it's somehow naturally dual to the Nouvelle one form. And so what these are is you take it's like a real foliation determined by the Nouvelle one form. So these are exactly the sort of analogs of things that we saw with the exponential networks and also yesterday with quantum periods and all those related. So all of those kind of geometric questions are very much related. Okay, so anyway, so these are the conditions. So you have this non-local assumption on completeness of the flow, and you have this regularity assumption. And then after a lot of work, you can conclude that under these assumptions, there are exactly two analytic solutions, S plus minus, for the Riccati equation with these fixed asymptotics. And the important point is that these fixed asymptotics are, well, uniform. Uniform is always nice, but it's in the entire right half plane. So how does this? Okay, so I could comment maybe more on this, but let me proceed. So how does this imply existence uniqueness for Wkb solutions? Well, remember the Wkb solutions are just integral exponential integral s. So if s is uniquely fixed, I'm just integrating it. So if I fix a base point of integration, then that should completely fix everything that I could possibly need. And indeed, so if you fix a base point x star, say in your domain U, then the conclusion is that you get a unique local basis of exact WQB solutions. Okay, so one thing I want to emphasize, so here I've just copied the theorem statement from the previous slide. One thing I want to emphasize is, well, two aspects. First of all, the uniqueness part of it is kind of important. That's certainly, you know, singular perturbation problems, of course, is such an old subject, and problems like this have been studied. But all the results that you find in the literature are usually nothing more than existence results. It's simply because, yes?
The right half plane refers to X.
Yes, no, right half plane H bar.
When you say the convergence is uniform, then it's usually uniform with respect to another variable, there is the one which converges.
So it's uniform in X, but it's also uniform in all directions in the right half plane. So by definition, what does it mean to take an asymptotic expansion in a sector? It means that in any smaller proper subsector, you have some bounds. So the statement here is that the bounds are uniform in that sector, in the entire right half plane. And this somehow, I mean, you kind of struck on the key point, because that is exactly where uniqueness comes from. It's the fact that I'm able to deduce this uniform asymptotic bounds in the entire half plane, that I'm able to eliminate any possible interference with like sub-exponential corrections that could interfere with uniqueness. So I mean, it's a very important point, because in some sense, this idea of uniqueness kind of, you know, one way to think about it is that the method for constructing these solutions is in some way optimal. It's optimal because, well, you know, I have a way to produce solutions in a unique way, and moreover, the method is so explicit that I get an integral representation for a solution. So these solutions S plus, they are literally defined as expressions like this. So there's the leading order part, which is kind of just entering on its own, but then there's a Laplace transform. So all these solutions are always Laplace transform of something. This function, of course, is very, very complicated. That's where all the complexity is hidden. But just to kind of give you an idea of how much handle you have on the properties of the solution is so this is how this is how sigma plus minus are defined. So again, it's kind of, there's an expansion. There's the sub-leading term of S, and then there's these phi's which enter into the definition. And what you have is that the phi's are just recursively defined. There's an explicit recursive definition of these phi's. So it looks maybe a little bit complicated, and I'm certainly not trying to explain the details of this formula, but I just want to show you how explicit the construction is. And so in particular, you could deduce various periodicity properties of solutions just by staring at this recursive definition. Okay, I think my time's up, so I should end here.
Thank you. Any questions?
So part of your theorem involves some restrictions for boundedness, so being local boundedness. Do those allow for apparent singularities?
Yes.
For you?
Yes. Indirectly, the way I would deal with apparent singularities is I would gauge them away. I would solve the gauged equation, and then I would gauge them back. And so, because I have this very explicit construction of the solution, the gauge transformation would also be very explicit. The resulting solution would be, you know, equally explicit. So.
So it's clear that the approach is intended for variational problems and such. So my question would be, is there any way that this can also be helpful in trying to approach the time-dependent problem or something like that, or?
Good question. Yeah, I don't know. Yeah, I really don't know. Maybe. Yeah. Maybe.
All right. There are no more questions. Thanks again.